So variance of the ordinary least square estimator, you can calculate it this way. The variance of beta 1 is sigma square, which is the error variance, right? Divided by SST, which is the just calculation of the xi minus x bar square, and then beta 0 will be calculated in this way. This is quite complicated here, but yeah. Sampling variability of the estimated regression coefficient will be higher, the higher variability of the unobserved factor, and the lower, the higher the variation in the explanatory variable. So meaning is here the sampling variability coefficient is higher, then you can tell the higher variability of the unobserved factor. So if this sampling variability is high, which means it's a high variability of unobserved factor, also has a high variability. Right? So if you have a high variable here, then unobserved factor also has a high. And if it's low, this is low. What does it mean? Is like an unobserved factor has a higher variability. That means it's because the unobserved factor, so SST plus S equals SSE plus SSR, right? So this is a kind of unobservable. This is our model. So this is just variable. So we can just compare the which one is this one has a variability, but this variability has a this one is higher or this one is higher. So we are just compared to this variable. Is this part is from this one, right? Because the sigma is errors variance, right? Errors variance, which is on observable factors, and this is a total. And again, this is a total, but now this has a x, right? Continuing having this one. So this is a more like a no. As you can see here, if you have a high variable here, which means this is bigger and bigger, then you have a low variability of your explanatory variable, but this one is high. So this one goes high and this one goes down, and this one goes high and this one goes down, because we are comparing to the SST here. Okay, how can you estimate the variance of error? So we even just say this will be the just sigma square. Again, this will not affected by the x, so you can just simply calculate the variance of the ui. So variance of ui is, you can just simply calculate it this way, right? So why this is the case is because indeed actually this is the biased. Why this is biased? Because u I hat is from the y I minus y hat, right? Which is the y I minus beta 0 minus beta 1 xi, right? Right. That's why you have this one, but why n-1 it doesn't work? Because here this is just average, right? But how many parameter we estimate here? So we estimate the beta 0 and beta 1 using this data. So we calculated the beta 0 and beta 1. Even though I use just this one, you had these two calculator you had. How many parameter did we estimate? 2 parameter. That's why you have to subtract 2, and this will be the unbiased estimator of the error variance. This is not -1. Again, why we have a s should be -1 sigma, right? And here this x minus x bar square, we estimate mu. So x bar is the estimator of mu, which is the mean population. So we estimate the one parameter here. That's why we subtract 1. Here, u hat, we estimate 2 parameters here. That's why we have to subtract 2. This is the degree of freedom. So you can simply calculate this, and then you can divide by n-2. Again, the reason is we estimate. To calculate this u hat, we estimate the 2 parameters. That's why you have to subtract 2. That will be the unbiased estimator of the variance of u. So theorem, the unbiasedness of the error variance is the of course this value, same way sigma hat square will be a lot, depends on the data. If you have a different data set, you have a different numbers. However, if you just calculate the average, if you just repeat the same thing, if this is a randomly selected data, this average calculation should be goes to the real population sigma 2. Okay. Unbiasedness of the error variance. So unbiased means is this estimator expected value will be the population. This is our estimator, and this is the value from the all population, right? This is all population. Expectation should be the same. That's on the definition of unbiased estimator. Okay, you can calculate the standard error. So we already seen the standard error. Previously it was like a SB1. That's the same as a standard error. It's a variance of the estimator. So which means we will estimate a lot of this one, right? If you collected a lot of data, first data will generate this one, and another data you can get one, and then most of them. If you calculate the average will getting close to the population error. Better. Actually, the population also has an error, right? So population regression line, and then that's what we gonna have. And then also the same thing, the standard error of the regression coefficients can be calculated this way. So estimated standard deviation of the regression coefficient is called the standard error. So this is the estimated standard deviation of the case. So what does it mean? If you can calculate the beta 1 hat many times, right, of the data, yeah, we don't have to calculate all of you don't have to collect the data again and again, but this is the what if we do it again and again, you can have you will have a lot of different number here. So we know average will goes to the real beta 1, which is a population regression coefficient. And then this variance is since this is a all different number, what would be the variance of this one? That's this one. This is a variance of the beta 1. Okay, so that depends on our error term here, divided by the SST. And same thing, we can calculate the standard error, which is since it's a square root, so this is like a standard deviation of the estimate of beta 0 will be calculated this way. So if you want to find out, and then if this is a small, standard error is getting small and small, which means maybe you collected a lot of data. Because of that, you can have a very small standard deviation, or your model, somehow I don't know the reason, but somehow the accuracy of the estimator is getting better and better. You will have a smaller and smaller standard deviation. Right? So they measure how precisely the regression coefficients are estimated.